Swayam Prabha. Digital India. Educated India.
Okay, so let me conclude. We have another 9 minutes. So let me conclude. So although we have seen things that seem very different from each other, there is something that's common. There's a common theme underlying all this. Let's try to look at that commonality to some extent. Okay, first of all, the data flow equations have a common form. So we have data flow variables defined in terms of xi equal to f of yi, and yi is equal to meet of xj. So because this could be both intersection and union, we choose a different symbol for it. Okay. Now this xi could be in I, xi could be out I. So xi could be in I, yi could be out I. Alternatively, yi could be in I, xi could be out I. Doesn't matter. But at an abstract level, it's still the same. So these are data flow variables representing data flow information. So far, we have seen sets or bit vectors. It could be entities other than sets. For example, it could be maps. It could be pairs. It could be functions themselves. It could be maps from one set to the other set. It could be graphs. It could be strings. It could be sequences. It could be anything. We have successfully used graphs as data flow values for performing liveness analysis of heat. So there can be anything. I mean, it's only we need to define certain mathematical properties of those domains of values. In particular, if you are able to define what is mathematically called a lattice, then anything that constitutes a lattice is good enough for data flow equations, for data flow analysis. Okay, we just have to satisfy the properties of a lattice. These are flow functions. So far, we have seen gen and kill that are independent of y. We could have gen and kill that are dependent on y. We could have very complex gen and kill. So the way for domain of values, we say we need to have a lattice. Here we say we need to have monotonic flow functions that are closed under composition. That's all that is required. We can define any function, we can define any value, so long as a value forms the set of values constitutes a lattice, so long as our functions are monotonic and they're closed under composition, we are good. We can perform data flow analysis using it. As you can see, this is a very, very general canvas. We have looked at very limited form of it. This confluence operation or the meet operation, so far we have seen union and intersection, but it could be other operations. What is the meaning of a union in case of a graph? What is the meaning of union in case of pairs? Or we could have a map from a variable to a set of variables. That could be the data flow values. For example, we compute pointer analysis. So we say this pointer holds the addresses of these other locations. So it's a map from a pointer to a set of pointers. It's a function from a set of variables to the power set of variables. Now, what will be the confluence in these things? It's not a simple union or intersection. It could be something else. It doesn't matter so long as it forms a meet operation of the lattice. So long as it forms a meet operation of the lattice, which means that the operation must be commutative, associative, and idempotent. And the lattice should be a set that has a partial order, which is reflexive, transitive, and antisymmetric. And once we have flow functions that are monotonic and closed under composition, these are the only things that we need for data flow analysis. Nothing else is needed. So what you can do with data flow analysis is only limited by these mathematical requirements. You can put it to a variety of different applications. Here is a classical taxonomy of bit vector data flow framework that we have seen. So we have seen union as a confluence. We have seen intersection as a confluence. There can be a forward data flow problem such as available expressions analysis. There can be a backward data flow problems such as live variables analysis, but there can be a forward union problem, which is reaching definitions analysis. Again, classical data flow analysis defined 40 years ago. We're not going to study it. There's another analysis called anticipable expressions. We're not going to study it. There's also something called bidirectional analysis, which is partial redundancy elimination. But then there are many more analyses in this category. For example, we have something called liveness-based points to analysis. So we perform liveness, we compute points to information only for the pointers that are live. So we have a combination of forward and backward dependencies. Okay, so so we have seen something that's very small. There is a very large and rich world out there. There are richer data flow analyses such as constant propagation, range analysis, pointer analysis, heap analysis, and many custom analyses. There's a very deep formal theory which involves lattices, properties of flow functions, abstraction and concretization functions to formalize soundness. We talk about efficient algorithms such as round-robin algorithm, work list algorithm, or summary-based elimination algorithms. And then the data flow analysis also studies efficiency and precision trade-off. For example, we can talk about path sensitivity, flow sensitivity, context sensitivity, field sensitivity, object sensitivity. We can talk about collaboration of different analyses. This is another interesting thing that one of my other PhD students is working on. Can we make analyses talk to each other so that collaboratively they become more precise? And then we have not talked about interprocedural analysis. What happens? A real program consists of many procedures. What happens when there are procedure calls? So we have something called top-down analysis, which traverses programs starting from main, going down to the callees. So this can be seen as a top-down traversal over the call graph, or there could be bottom-up analysis, which constructs summaries of the callee procedures and puts summaries back in the bodies of the caller procedures, and we perform interprocedural analysis. So interprocedural analysis is another interesting topic of active research in our group. So there's a lot. I mean, there's much more that we have not covered than we have covered, but I'm hoping that I have been able to give you a flavor of what data flow analysis is all about. And that is what was the goal of this tutorial. And I hope you have got a taste of what data flow analysis is. I will be happy to take questions. I'm glad I'm finishing on time, but I'm available for questions if you have any.